Have you ever wondered how fast you can draw bunnies to the screen? Neither had I until I stumbled across Raylib's Bunnymark example. Its true purpose is to introduce drawing textures to the screen, which it does wonderfully. However, I was quickly distracted by potential optimizations. Not of the actual drawing, which is the current bottleneck of the example, but of the position calculations for the bunnies as they bounce around the screen. Or, in the case of my re-implementations, the circles, which are close enough to spherical cows. Given the straightforward logic, both aspects could be improved simultaneously by handling it all on the GPU. But the potential for auto-vectorization of the CPU code is too intriguing to ignore, so perhaps the GPU changes will have to be for another time. Going down the CPU rabbit hole, we'll actually find that such calculations can be improved nearly fourfold, all while keeping the logic single-threaded and as portable as possible. Better yet, the ideas we'll cover are applicable to more than just a toy example, and should give helpful considerations for any future projects. As a quick primer, auto-vectorization here refers to a compiler's ability to generate special SIMD instructions to operate on multiple pieces of data simultaneously. If a single instruction can work on multiple data, then it naturally follows that less instructions will be used as compared to processing one element at a time. For example, consider incrementing an array of numbers all by one. With traditional scalar code, for each number we might load it into a register, perform an add operation, and store the result back into memory. With SIMD instructions, we can load multiple contiguous numbers into a larger SIMD register, where a vector add operation can process those elements all in one go, and then store the result back to contiguous memory. The exact capabilities differ by hardware, and even focusing on x86, there are various instruction sets such as SSE, AVX, and AVX512. Modern systems can often use up to 512-bit SIMD registers, and can operate on as many as 16 single precision floats at a time, though with the caveat that these numbers need to be contiguous in memory to efficiently load these registers. To see this in action, let's go back to our kinematic example, but simplify it a touch more to only moving points in one-dimensional space. The general concept remains largely intact, and we'll be able to more easily observe any differences in the generated assembly as we make changes. To start, we of course need a way to represent a point, which is easily enough done with a struct that has a position and a velocity. Going from one point to many can be as simple as using a stood vector of these points. To update each, we can use a range-based for loop and increase a point's position based on its velocity and some change in time. Keeping things simple, we'll use a constant delta time, but having it will let us see an important optimization later. Adding one last bit of complexity, we'll also implement some basic bouncing. If a point is moving out of the range between 0 and some constant, all we need to do is reverse its velocity. Obviously, the code doesn't compile exactly as is, but the rest of the details aren't particularly important for what we want to observe, so here it is in full. We of course have our includes, and we'll be putting everything into our main function. We still have the same constants that we were using, but also introduce some rudimentary command line parsing that will use control number of points and iterations for a timing loop that we've yet to see. Next, we have the familiar point structure and our vector of points that we're now populating with some not-so-random values just to keep the compiler from optimizing all the logic away. Finally, we get to the aforementioned timing loop that'll make it easier to compare changes to the performance of the update logic we've already seen. Though really, it would have been better to use a proper benchmarking framework. With something that now compiles and runs, we'll see that it's actually quite slow at nearly a minute. Or I guess without any comparison, the result doesn't say much yet, but being slow with no optimization at all shouldn't be much of a surprise. If we take a look with the profiler, we'll see a significant amount of time is just spent on iterator functionality. We could drill in deeper, but let's carry on to a more reasonable compilation. O2 is a fairly common optimization level for G++ and turns on most optimizations that don't involve a space speed trade-off. Running the program now results in a much more reasonable execution time of roughly 5.5 seconds. Using a profiler again, we can start to dig into the assembly. While I do find it intriguing, we don't need to understand all of this line by line, but rather observe key instructions and how they impact our performance. First, we can focus on the lines with a higher execution percentage, though I'll note that since we're using a sampling profiler, the exact lines should be taken with a bit of leniency. Either way, there's a clear loop that seems to encompass these lines, which should roughly place us where we expect to be. Sure enough, we can find a multiply and an add instruction that's familiar to our logic to update a point's position. Interestingly, they are SSE instructions, as compilers often assume at least SSE2 support for 64-bit x86 code, but they are the scalar variants as denoted by the first S in the SS suffix, so we're still only processing one point at a time. Going a step further, we can take a look at one more optimization level with G++'s 03. Somehow the compiler manages to shave off roughly half the time already, so let's take a look at the assembly. We've got quite a bit more relevant information to look at, but if we again focus on our familiar multiply and add, we can see that they are now the packed variants, which simply means that we're taking advantage of processing multiple elements at once. These particular instructions are using the XMM registers, which load 128 bits, or 4 floats at a time. But how is that possible if values need to be contiguous in memory while our position and speed values are interleaved? If we look around, we'll find a hint with commands like shuffle and unpack. We again don't need to fully follow the logic, but the compiler can generate instructions to load the variables into SIMD registers together and shuffle them around as needed for the actual math operations. Storing the values back to memory requires a bit more finagling, but the overhead is clearly worth it as we did get better performance. What if our machine supports larger SIMD registers? While we've seen SSE instructions emitted by default, anything more will require telling the compiler what's safe to use with compiler flags like MAVX. This could lead to maintaining separate binaries, or more likely code paths, for machines with various configurations. That could be another topic in of itself, so we'll focus on the easier scenario where we compile for a given set of capabilities. To make it particularly straightforward, we can use the march flag to specify a CPU type, which will enable all the relevant flags for us. Specifying native is often the most useful, as it'll determine the CPU type of the machine compiling the code, which is often where you want to run the code as well. To keep it easier to follow along, I'll explicitly specify Zen version 4 for our example system. With our new flags, we can see that we managed to nearly double performance again, all without changing the code at all. Drilling in as usual, we're greeted with plenty of new instructions, and most importantly, plenty of usage of ZMM registers. The nomenclature here is that XMM registers are for 128-bit instructions, YMM registers are for 256-bit instructions, and ZMM are for 512-bit instructions, which means we're up to processing 16 floats at once. Though with speed and velocity values still interleaved, we continue to use shuffling of sorts, though now that's done by the permute instruction. Our familiar multiply and add instructions have also combined into a fused multiply and add, further improving performance. Another observation that becomes even more important is that there are no guarantees that we have 16 values to process, so there needs to be some logic to ensure that we don't read or write past our actual data. Often this leaves logic like here, where we process the tail of computations, with instructions working on registers with smaller and smaller width, going from 512 to 256 and eventually scalar operations. Hopefully this first set of comparisons demonstrates the power of optimization flags and what happens when a compiler is able to auto-vectorize your code. Even ignoring the unrealistic absence of any optimization, we were able to see a roughly 4 times improvement in execution speed, all without changing any code. Before we get to further improvements, it is worth demonstrating, however, that our toy example may be inflating these results a tad. If we look back at our structure for a point, we have a very simplistic data type that often isn't what you end up seeing in real-world applications. Even if we keep all the logic the same but just pad out the data type, we can see that it's quite easy to end up with a program that isn't as conducive to auto-vectorization. Even with our best optimization flags, we're now nearly at 15 seconds of execution time. Some of this surely can be attributed to other factors, like the cache misses we've certainly introduced, but the assembly shows that sure enough, we're back to scalar operations. If it's so easy to hinder auto-vectorization, is there anything we can do to make it better? Of course we can, and it all comes back to the fact that SIMD registers are loaded from contiguous memory. Instead of interleaving values in a struct, we can instead keep track of parallel arrays. This changes how we access values and removes a convenient range-based for loop, but conceptually all the logic continues to remain the same. A quick compile is followed by a quick execution, as we find ourselves with another doubling of performance. Sure enough, diving back into the assembly, we find packed vector instructions as we expect, without a shuffle or a permute in sight. We do still have tail calculations that use smaller SIMD registers and even scalar versions of the code. This isn't always an issue, but can contribute to larger binaries and potentially regress performance. Our toy example isn't complicated enough to show such an issue, but we can take a look at another approach that mitigates it. We only have these tail calculations since we can't guarantee that for every iteration there's always enough data to fill a full-size SIMD register. Conceptually, the solution is straightforward enough, as we can just over-provision to always use memory that is an exact multiple of SIMD register widths. There are multiple ways to implement this, but an interesting one is a hybrid of the previous solutions, where we have multiple parallel arrays for position and velocity. Using an array size that is equal to, or at least a multiple of, SIMD widths, ensure there's always memory to read or write to. 512 bits can hold 16 32-bit floats, which of course also fits evenly over multiple 256-bit or 128-bit registers, so is a natural starting point. This does mean that we now have two sizes to keep track of, how many points are safe to process, and how many of those points we are actually using. Whether the additional complexity this adds is worth it depends on the rest of the project, but here we can see that we still have rather nice performance. Unsurprisingly, this means that we are still using packed vector instructions, but we'll also find that we fulfilled our goal of removing any tail calculations, making for a shorter assembly listing. While perhaps going one step further than I originally intended, there is an easy improvement from here that's worth pointing out. So far, we've been focusing on if SIMD instructions are being used, and if they are the scalar or packed variants. When loading values into SIMD registers, however, there's another dimension that can be worth noting. So far, we've only seen unaligned loads, but if the data meets extra alignment requirements, such as being aligned to a 64-byte boundary on AVX512, an aligned load can be used instead. The performance implications aren't as straightforward, but for this toy example, on this particular AVX512 system, it's a noticeable improvement, though not quite at the same scale as everything else. And with that, I'd say we're at a good stopping point for this particular rabbit hole. SIMD instructions can clearly give a significant performance boost, especially when paying attention to data layout and compiler flags. I have a feeling this isn't all this toy example can demonstrate, so I'm curious what other topics folks may be interested in as well. We've already mentioned GPU optimizations, but even on the CPU, there's still much to explore. Then of course, there's the potential to investigate other architectures, frameworks, game engines, and the list goes on. So until next time, take care.